So today we're going to talk about sort of a cosmic perspective and what is space and where is space. And this corresponds with Chapter 3 in your book Understanding Space, the Jerry Sellers book. I've noticed that a lot of the material corresponds with the book, but we've given you some supplemental material. This one fits in with that theme. So most of the material's in the book, but I've expanded a little bit and emphasized some parts of the chapter and de-emphasized others, but this roughly corresponds with Chapter 3. So a couple of real basic questions we're going to deal with today. What is space, where is space, and what's in it? And by implication, why do we want to go there? So the first question is to answer is, where is space? How do we define where space is? Up, okay. How high up? How high is up? Outside the atmosphere, okay. Where it starts getting cold, okay. The interesting thing about the atmosphere, it starts getting cold, then it gets kind of warmer again in the troposphere, then it gets colder again. If you were in Space Trek, you probably learned that, but you weren't Space Trek because it's just for girls. So those are all good ideas. How high does the atmosphere go? It's not an easy thing to define. I mean, the atmosphere, does it stop? Is it like a blanket? It just all of a sudden stops? Or does it make a gradual transition into interplanetary space? It's a pretty gradual transition, right? So how do you define where the atmosphere ends? How do you define where space begins, the atmosphere ends? And maybe it's not just the atmosphere. The influence of gravity you can't really think about because it extends forever. It decreases as a function of the square of the distance as you go farther and farther away. But gravity is not a really good way to define where space is. Magnetic field of the Earth extends also out, and we'll see it gets pretty complicated. So it's not a really good way to define where space is either. So you guys are hitting on the right direction, is essentially where the atmosphere ends. But that's a complicated thing to determine where the atmosphere ends. I mean, once you go to 1,000 kilometers, there's basically no atmosphere at all. But at 600 and 700 kilometers, there's not much atmosphere, but there is what we refer to as a ballistic atmosphere, because there's enough particles, believe it or not, of atomic oxygen and hydrogen and ions to actually induce drag on the spacecraft. And we have to account for the ballistic atoms and molecules even at those extreme high altitudes. So how do you define where space is really not easy. And because it's not easy, there is no uniformly accepted definition of where space begins. But I can tell you it's closer than Lexington. So a couple of ways to define it. You can get your astronaut wings at 80 kilometers. My wife Jen has actually just returned from the Sophia flight to 45,000 feet, so she didn't quite get her astronaut wings, but she was up there. You could see the curvature of the Earth and the blackness of space above. So that was pretty cool. She was on the Stratospheric Airborne Infrared Observatory last night. But anyway, she didn't quite get her astronaut wings because you got to go to 80 kilometers to get your astronaut wings. So extremely high altitude and experimental and military spacecraft can get to those altitudes. We don't know what the top end of some of the spacecraft is because it's not known to normal people. But anyway, you can get your astronaut wings at about 80 kilometers, which is about 50 miles. The definition I like is the von Karman Institute line. Bob actually works with the von Karman Institute in Belgium quite a bit on some of their small spacecraft work, but 100 kilometers, which is about 62 miles, is the von Karman definition. And we've also used it, interestingly enough, as the X Prize definition. Do you guys remember the X Prize a few years ago when there were a few entrepreneurs that got together and produced a $10 million prize for the first private company that could build their own spacecraft and get to space and come with a person, bring it back to Earth, and turn around and do it again in 2 weeks. And who won the X Prize? SpaceX won the X Prize. That's exactly right. So they sent an astronaut to space in a privately built spacecraft. They built it essentially in their garage. I'm exaggerating a little bit, but but at the time they were a very small company. And so that definition for the Ansari X Prize was the von Karman. They used the von Karman definition of 100 kilometers. So how many people have been to space? then. Not just the, if you use the von Karman definition, not just astronaut wings. Take a guess. How many astronauts have there been in space, in low Earth orbit specifically? 30, okay. A little bit higher. 100, a little higher actually. It's close to 500 now. So about 500 astronauts. If you count all the shuttle pilots, the Apollo, the Gemini, all the international flights to Mir and to International Space Station, about 500 people or so have been to low Earth orbit. So we're not new at this. But for our purposes and for all practical purposes, you got to get up a little bit higher to stay on orbit. Once you're above 130 kilometers and you have circular velocity, then you can stay in space and orbit indefinitely. Now, for all practical purposes, if you're at 130 kilometers, you're going to come down very, very quickly. When you get up to the International Space Station altitude, and what altitude does the space station fly at? Varies a little bit, but roughly. What do you think? 350 kilometers. So it's pretty low down, but it's basically out of the muck of the atmosphere. So once you get up there, you can orbit, for long periods of time. But still not indefinitely. They're always having to nudge the space station up and down because the space station, there's enough atmosphere, believe it or not, at 350 kilometers to create a drag effect on the International Space Station. So often they're having to nudge it back up. And if you eject spacecraft, small satellites from the space station, they might only stay in orbit, maybe something like a month to under a year. So the higher you go, the longer you can stay. But once you get to 1,000 kilometers or so, there's essentially no atmosphere left, and you're up there indefinitely. There's effectively zero ballistic drag at 1,000 kilometers. So it's kind of complicated to determine where space is, how high do you have to get to stay in space. Depends on lots of different things, like the ballistic coefficient, the drag surfaces of the satellite, the mass of the satellite. So a lot of things to consider, and of course, where you want to be in space depends on what your application is, what you want to do. If you're Earth observing, if you're looking at GPS systems, the specific applications determines where you want to be. But anyway, space, however you define it, it's you're going farther when you go to Lexington or to Huntington than when you go to space. Believe it or not, it's harder to get to because how do you get to space? What's the old joke? You just go straight up 100 miles. Harder to get to, but very close. Okay, so I think we've sort of covered, this is a sort of graphical representation. It's actually a little bit misleading because the curvature of the Earth would be almost flat at that scale. And when you're looking at, a picture of the Earth with the space shuttle on orbit, it's almost, it looks like it's on the surface of the Earth. But again, about 100 kilometers is the von Karman definition. So that's answers the question, I think, at least to some extent, of where is space. But really what I want to focus on today is what's in space. What's in space worthy of scientific investigation or worthy of study? So what is it? And these are some questions we want to sort of address today. So is space really empty? We know it has matter, some matter there. We talked about some of the particles that are in space. We know there's energy in space. So what about the matter and energy in space? Is space continuous or discontinuous? In other words, can you chop it into little pieces? I can look in any direction in the universe and see just about as many galactic clusters in one direction as I see in any other random direction. So it's really a function of scale whether you define the universe as homogeneous or inhomogeneous. So I add a little bit of detail there. The universe have an end. We know it had a beginning. Does it have an end in time and an end in space? So these are kind of cool questions, I think, that are on the interface of astronomy and astrophysics and space science that are kind of cool to think about. A couple others: is matter hierarchical? In other words, is it made of little things that stick together to make big things, or is it just homogeneous in its internal structure? And what's the role of the fundamental forces, and do the laws of physics apply pretty much everywhere in the universe, or are they unique to different regions? So just a few simple questions we want to try to answer today. Okay, so that was a joke. And I should probably mention at the very beginning that if you don't think I'm funny, it'll be a really long hour. And that's about as funny as it gets. So we're in trouble. It's a tough audience. Yeah. Yeah. Full of something. So here is the universe in a nutshell. We know there's matter, right? And we know there's energy. But there's this thing called dark matter, and there's another thing called dark energy. And they all sort of exist together within the context of space and time. And it turns out space and time really aren't separate physical things. They're actually different aspects of the same phenomena, believe it or not. So they're intertwined, they're interconnected in ways that you might not think that are conventional. But we have normal baryonic matter, that is to say the matter that's made of protons, neutrons, and electrons. And then we have energy that you know about. There's electromagnetic energy. There's other forms of energy we'll discuss, and they're governed by the fundamental forces. But then there's these things called dark matter and dark energy. And why do they matter at all? Is there enough of dark matter and dark energy to even worry about? There's more dark matter than there is matter, by far. That's exactly right. What about dark energy compared to matter or energy? Same thing. There's much more dark energy. Why does it matter if there are these exotic things in space? What does it matter to you if you're developing a spacecraft? It could interfere. It could interfere with your observations. That's an excellent point. When you go great distances, believe it or not, you have to account for the dark matter component of different masses, because there's a matter component, a dark matter component. So there are lots of reasons that spacecraft developers need to understand the underlying physics of the universe to some extent to account for these different phenomena in the design of the spacecraft. So believe it or not, most of the entire universe is not made of normal matter that makes up, dogs and the desk here and people and the atmosphere. That's the normal matter, the baryonic matter that you consider sort of normal. That's actually exotic in terms of a statistical sense. Something like between 2 and 6% of the entire mass of the universe is dark matter, or is normal matter. The rest of it is dark matter and dark energy combined. So there's really very little normal matter in a statistical sense. The way I kind of think about it is I use a lot of sort of ocean analogies because I grew up on the East Coast on the beach, and I love the ocean. And have you ever been standing at the beach and looking out at the ocean and noticed the foam on the top of the ocean? That's essentially the baryonic matter, and the deep dark ocean itself is dark matter and dark energy. Okay, yes sir?
Do we know anything besides that it exists about dark matter and dark energy? Are they like broken up? Like we can categorize
yeah. So that's a really interesting, the question is, what do we know about dark matter and dark energy? First of all, let's take just a minute, and you guys interested in this kind of thing? Because I've got a lot of material to go through, and we might not quite get through everything if we diverge a little bit, but this is kind of an interesting story. So what do we know about dark matter and dark energy, and how do we know they even exist is sort of, I think, an interesting question to think about. Let me turn this off for just a minute. We've known about dark matter since the 1970s. We've only known about dark energy since about 1995, and really since about 2001. The dark energy component of the universe has been real obvious. People started to figure out that there was dark matter around in the 1970s when they were looking at galaxy rotation curves. And for example, if you look at a normal galaxy, like a spiral galaxy, and if you look at how its rotational velocity works as a function of distance from the center, it should be more or less Keplerian. In other words, well, let's think about this. You tell me about the solar system. Who's moving fastest in the solar system? Which planet? Mercury. So if this is distance versus velocity, the inner planets would be moving at a fast velocity, short distance. Who's the slowest planet? Neptune. So it goes way out here. And so if I plotted a velocity distance curve for the solar system, it should look sort of like that. It should tail off. Well, guess what? Before the 70s, when we were doing a lot of galaxy surveys, not me, because I was little in the 70s, before astronomers were doing this kind of work, we assumed that galactic rotation curves would be Keplerian in nature, just like the solar system. So as I get farther and farther, because most of the mass of the galaxies is in the black holes in the center of galaxies, right? So we can find extremely high velocity stars in the interior, and as you go farther and farther out, the expectation was that the stellar velocities would go down as a function of distance. Well, guess what? When they started being able to measure velocity curves for galaxies, they noticed they weren't really going down. In fact, at the luminous disk of the galaxy, they weren't going down at all. In fact, they were usually going up instead of down. So, well, if you have one galaxy or two like that, it's not a big deal. In the 70s, there was a group of astrophysicists led by Vera Rubin at the Department of Terrestrial Magnetism, one of my heroes. And she and her group measured the velocity profiles for thousands of galaxies. And guess what the rule was? The velocities go up at the edge of the luminous disk. Isn't that crazy? So what does that mean then? That means that there's more mass outside of the galaxy that you can't see than there is inside of the galaxy than you can see. If you add up all the mass, because you can measure the mass of the stars, right? Even if you have two things that are co-orbital, and you know the orbital period and you know the separation, it's just a matter of basic physics to determine the mass of those two bodies, right? So we can measure the masses of stars easily. So we can add up all the mass of the gas and the dust of the stars in these galaxies, and guess what? They didn't account for the viral mass that you could see in these curves. In fact, they only accounted for a fraction, something like maybe 5%. So we knew then, as early as the 70s, there was a whole lot of material associated with galaxies that was completely invisible in every part of the electromagnetic spectrum. You can't see it in light, you can't see it in infrared, can't see it in the X-ray, you can't see it anywhere. Of the four fundamental forces, it only is evident through gravity. So it seems to only interact, dark matter, with a gravitational force. So now we have to invoke what we call dark matter halos for the physics of galaxies to work out. So since the 70s, we've measured thousands, tens of thousands of galactic rotation curves. And they all essentially have the same patterns. So now we know that most of the matter in a typical galaxy is not in the stars, and it's not in the gas and dust in between the stars. It's actually in the dark matter components surrounding the stars, right? So I won't go into, so that's dark matter. That's how we know dark matter. What's it made of? We have no clue. To answer your question. That was a long answer, sorry, to a simple question. We don't really know what it's made of. We know it's there because we've measured it. We're starting to measure the distribution of it now, but what is it really? We just don't really know. It could be that neutrinos, there are flavors of neutrinos that have additional mass that we don't understand. There could be subatomic particles that we haven't discovered yet. It could be black holes, small black holes that we can't see surrounding the galaxy, but we just don't know. It is up to the future generation of scientists and engineers to answer that question. It won't be my generation that answers that one. It'll be you guys. Exactly. So that's dark matter. It's a really interesting notion, and it's there, but we don't know what it is. Question?
Do we have any around our solar system?
Yes, we think that dark matter is everywhere. It is everywhere, maybe in this room. It certainly is not just at the scale of galaxies. It's most easily measured at the scale of galaxies, but it seems to be everywhere. There is dark matter in the solar system. Yeah. There's an experiment on the International Space Station called the Alpha Mass Spectrophotometer, AMS, and it may have captured the first piece of dark matter. We don't know, but there's some research you can read. It's kind of preliminary, so I won't go into it today. But it's possible that this particle physics experiment on the International Space Station has actually contained a piece of dark matter. And if it has, that's a huge, huge discovery. So it's kind of weird, huh? It's nothing like dark energy. If you think this is strange, dark energy is like science fiction strange. So how do you explain dark energy? It was about 1995 we started to measure the expansion rate of the universe in past epochs. And how do you do that? It's a little bit complicated to go into, but just as a brief overview, we look at a type of supernova in the universe called type 1a supernova, and they all have about the same brightness. So I can actually measure the distance to a type 1a supernova, so they all have the same brightness, and one looks dimmer apparently, and one's brighter. I know the dimmer one's farther away, right? So it's kind of a standard candle that we can use to calibrate distances in the universe. So when we started trying to look at type 1a supernova in the late 90s and early aughts to try to measure the rate of expansion of the universe in the past and compare it to the future, or to the current, and project to the future, we found something really weird. So there are three possibilities. We know the universe is expanding outwards. Okay, the universe is, how old is the universe? You guys tell me. About 13.5 billion years, right? Exactly. So there was an event called the Big Bang. We're still in the middle of it. You can't think of it as a past event because it occurred 13.5 billion years ago, and the universe is expanding outwards in all directions now. Well, there are three possibilities for that kind of dynamical universe, right? It could expand forever and ever and ever, right? It could reach a maximum radius, and then the mutual gravitational attraction of all the galaxies could pull it back together. It could undergo a big crunch, right? And then the other possibility is kind of bizarre. It could expand but slow down and stop after an infinite time of infinite expansion. I'll let you think about that one over your Cheerios tomorrow morning. And the three ultimate fates have completely different implications for the ultimate fate of the universe and the ultimate fate of the solar system, the sun, and everything. It's kind of an important question. Yes, ma'am. So that's a really good question. So Olber's paradox is the idea that the universe should look really bright, but it doesn't. The Olber's paradox basically says that when I look into the night sky, it shouldn't be dark, it should be bright. Because every line of sight I can possibly imagine, if the universe is infinite or quasi-infinite, should end up on the surface of a star, stars are incredibly bright. So everywhere I look, I should be looking at stars. What we've discovered later, though, about Olber's paradox is it didn't take into account the fact of the intervening interstellar and intergalactic medium. So there's this attenuating medium in between the stars and in between the galaxies that attenuates the light and makes it dimmer and dimmer and dimmer as you go out. So we think we've sort of solved Olber's paradox to some extent, but it led to all kinds of neat discoveries about star birth and stellar evolution. So it's really still a very interesting topic. Good question. So before 1995, astronomers really fell into two categories. Categories of astronomers that believed that the universe would reach a maximum size and collapse in on itself and start the whole thing over. I was one of those, because think of what a beautiful philosophical idea that is. Not that the universe, gets destroyed in a giant crunch, but what could happen after a big crunch? You could have another Big Bang and recycle the entire universe. All the stars are going to burn out and die anyway, right, and take the planets with it. So, things die. There's a law of thermodynamics that tells you that. So if things are going to die anyway, it would be nice to be able to start things over. So for me, it was a beautiful idea from a philosophical standpoint. They could have an oscillating universe, one that starts over constantly. So I was in the camp. I wanted hard for the universe to stop expanding at some point. And there was a small group of astronomers, however, that didn't believe the data at the time. And this is the wonderful thing about science. Nobody believes anything. You got to prove it. Science separates itself from other disciplines because it's sort of built-in empiricism, because nobody believes anything. Show me the data. I got to analyze the data myself. You got to prove it lots of different ways by different groups. Nobody believes anything until the data become compelling and you can prove something over and over for many years in different ways by different people doing it. So there's an inherent set of checks and balances that most other disciplines lack, and that's why science and engineering are the most important and useful disciplines in the history of humanity. Okay, I kind of forgot where I was going with that. I got on a little soapbox there for a minute. But okay, so the other idea is that the universe expands forever, right? Or it stops after an infinite time. But think about how unfriendly, unhappy that is for an end of the universe. All the stars burn out. Stars give off light, so they have to have fuel. They have a finite amount of fuel. So every star has a finite lifetime, right? And there's only so much hydrogen and helium that are free in the universe to start new stars with, right? So when you run out of all that hydrogen and helium to start new stars, then the universe goes downhill in a hurry, because it has made all the stars that it will ever make, and then they're going to burn out, and the universe ends in a cold, lifeless, arid death. But it's even worse than that, because superimpose on top of that scenario the expansion, and the cosmological expansion gets worse and worse and worse, so things get incredibly far apart, and things fall apart because of the second law of thermodynamics, and then they grow old and get cold and die, the end. Now, which universe would you rather have? One that could recreate itself, or one that ends in a cold, lifeless death? Well, guess which we think it is now. When we were able to finally measure the Hubble constant, the expansion rate of the universe in past epochs, it shocked everybody, because not only is the universe not slowing down like I had hoped and thought it would, it's not even moderating, it is speeding up. Nobody expected that. That's right. That's exactly right. But okay, so that is, have you guys had calculus yet? That's, okay, the first derivative. The second derivative is what's that doing, right? So not only is farther out you go, the faster it's moving, but the whole thing, the whole system is actually speeding up. So over time, so now invoke, what you said is exactly correct, but now think about another layer of that. Over time, that whole system is speeding up. So the farther out you go, the faster things are moving, but over time they're moving faster and faster and faster. It's going to expand more and more and more and more and faster till things get so far apart that nothing matters. The one atom will be the entire universe for all practical purposes at some point. Nobody expected, but guess what? That's what we think now. As bizarre as it sounds, that's what we think. Yes, ma'am?
Are there theories that there's more than one universe?
There are multiverses and brain theory, and it turns out that laws of physics do not preclude the existence of multiverses. As crazy and bizarre as that sounds, people have worked out the physics and the math behind, could this be the only universe? Is it, or could there be other universe in, outside this bubble of the universe? And it turns out that nobody has disproven yet, with any of the laws of physics that seem to work, that multiverses are not possible. So it's certainly possible that there are other multiverses. But to get back to answer the question, and that's really an interesting idea. That's another topic, another lecture, which we can do sometime. What's causing the universe to expand outward, to accelerate its expansion? Dark energy. That's exactly right. You could think of it as kind of an anti-gravity thing. It's this dark energy component of the universe that's making things move faster and faster and faster apart. And we don't really know what dark energy is, but I'll tell you what the theory is. And the theory is, if you think what we talked about so far is bizarre, here's the theory behind dark energy. What's in space? Well, you guys, what do you think? Is space empty? We know locally it's not empty, where you have gas and dust and stars and planets and asteroids. But what about interstellar space? The space in between the stars? Not empty, it's got gas and dust. What about intergalactic space, when you're talking about really vast distances of space where there's just not much matter, if any? Still, there's stuff. And here's what we think is the stuff. If you take a cubic meter of intergalactic space, we believe that there are virtual particles that create and annihilate themselves out of nothing. And that creation and annihilation of virtual particle pairs creates a dark energy component of the universe. So even intergalactic space is not empty by any stretch of the imagination. And there's a mass energy component of the universe that's constantly being created and recycled in the fabric of space itself that gives rise to this phenomenon of dark energy. Wow. Does it sound like science fiction? We've measured it since the late 90s. And the more precise measurements that we make, the more accurate the theory seems to be.
What is that break? Like
conservation laws? Yeah. No, it's actually consistent with conservation laws, because we can measure the total mass energy content. So you can measure, you got two sides of the equation, right? You got mass energy on one side, you got to have something producing it on the other side. And whether it's mass going into energy and energy going to mass, it doesn't really matter. The final answer is that they balance. So there's no violation of conservation. Yes, ma'am.
Could this dark energy be an area of physics of the universe that we haven't discovered yet?
So now that brings us back to another idea. Did you guys all hear the question? Could the dark energy just be an area of the universe that we haven't discovered yet? Sorry. The answer is we think probably not, because the thing is, we've been able to measure dark energy throughout the entire visible universe. So we're trying to, in fact, that's how we sort of discovered that the universe was expanding, was we were trying to measure the expansion rate in past epochs by looking at different places in space. And so we think, for the most part, that the laws of physics are ubiquitous. That is to say, they apply everywhere. So the same laws of physics that apply here on Earth apply in a distant galaxy, apply in the most remote regions of the universe. And it's a good thing, because it'd be hard to predict anything about the universe or understand anything about the universe if that were not the case. But the thing is, you look at the most distant stars and the most distant galaxies you can find, they're made of the same materials. They're made of hydrogen and helium, lithium and beryllium. They seem to act the same way. Gravity seems to act the same way. Electromagnetism seems to act the same way. So it's a wonderful thing that the laws of physics seem to apply everywhere in the universe and in all times, both past and current epochs of time. So that's a good thing. Okay, so dark matter, dark energy is weird, but you know, that's what space is made of. So let's go through and do a little bit more in terms of some of the details. Let's take a little bit of time and talk about the rest of the normal matter. How do you make all that matter? You know, we've got galaxies and we've got planets, we've got stars, we've got asteroids, we've got all these things. How does it all work out? How does it all fit together? Well, it turns out that you can break everything down into very simple components. You can build things up in very complicated ways, but there's this idea in physics that things are very simple at the most fundamental levels. And in fact, we have boiled the entire universe down to basically energy that's governed by 4 fundamental forces and just a handful of particles. And you could think of as basically as few as 3 particles. It's a little bit of an exaggeration, but it's not too inaccurate to say that. So what I really want to do is tell you about the forces and the particles that make up everything and how that works. So going back to the question, is matter continuous or discontinuous? So let's say I take a rock, an asteroid, and I chop it into little pieces. And I take the pieces and chop them into little pieces. How much chopping can I do? Is there a point where I have to stop chopping and I reach a fundamental component of matter? Or can I keep chopping forever and ever and ever and there is no fundamental point at which I have to stop chopping? So if it's continuous, I can keep chopping forever and ever and ever and I don't find anything that's a small unit or building block. If it's discontinuous, I reach a point where I have found the simplest, most fundamental component of matter that I can possibly find.
Technically, you probably could.
Okay. Currently, we think it is discontinuous, right? So what is the small? If that's the case, then what is the smallest, most fundamental component of matter? Quarks. That's right. So they're not atoms. I was trying to trick you guys, but you're the smart kids. I can see that right now. I really do that. So yeah, I can take that lump of asteroid and I can break it into molecules, and I can break down the molecules into atoms, and I can break down the atoms to the subatomic particles that you see here in the atom. But I can actually break down at least the nucleons in the interior of the atoms, the protons and neutrons, into the most fundamental components or fundamental units of matter that currently are thought to exist, and those are called quarks. So what I want to do is take you through this sort of hierarchy of the distribution of matter for just a minute, and basically try to answer, what's the universe made of, and how's it all put together in 5 minutes or less. I can't turn one of these off. I have to turn them both off. Okay, so let me walk you through what we call in physics the hierarchy of matter in the universe. And basically, what's in the universe is the question. So the most fundamental components in the universe are, you guys have already said, are quarks. And anybody know how many flavors of quarks there are? There are 2 that are common. That's exactly right. There are actually 6 flavors altogether. Can anybody name the 6 flavors of quarks? I'd be really impressed if somebody could. What about the 2? What is it? Up and down, strange and charm, and top and bottom, or above and below, top and bottom. Wow, okay, dang. So you got up, down, top and bottom, and strange and charm. And only two really exist in any major quantities in nature anymore, which are ups and down quarks. We've discovered, I believe, 5 out of the 6 now. Produced them in particle reactors like CERN and Fermilab. But the ones that really matter are ups and downs for the modern universe. You can find the other ones. They're in exotic high energy situations like accretion disks associated with black holes, or pair annihilation events when material gets annihilated under different electromagnetic circumstances. You can find the other flavors, of course, but they're not very common. But ups and downs are common because they make up the subatomic particles. So the subatomic particles, that is to say the particles that are smaller than the atom, are of course protons and neutrons. Actually, I really need to add something to the quarks. The quarks plus leptons are considered fundamental in nature. Leptons are a group of particles. All this is in the standard model of subatomic physics, by the way, if you want to find out where to find all this material from sort of the subatomic level down. Leptons are like a flavor of, a lepton is an electron that you're familiar with. They're also positrons, and there's a variety of different leptons, 6, but for practical purposes, they're like electrons. So electrons really are considered fundamental, right? Because I can't break an electron down into a smaller particle. The protons and neutrons, however, I can break down into quarks. So for example, a proton is 2 ups plus 1 down quark, and what do you think a neutron is? 2 downs and an up, exactly. Okay, so the subatomic particles, if I lump those guys together, what do they make? Atoms. And if I group atoms together, group of atoms are called molecules. And what can I make with molecules? Huh? What? Elements? Well, elements really would be considered at the atomic level, because elements are groups of atoms that are all sort of the same. A molecule is a group of atoms that might not necessarily be the same. I'm going to use a highly scientific word here. Stuff. All stuff is made of molecules or atoms. You might see it as matter in various textbooks, but just so you know. And if I have a bunch of stuff in one place and it's all gravitationally bound together and it's separated by distances, great distances of space from other stuff, I might call it a planet. And do planets live by themselves, or do they live in groups? They live in groups. What do we call groups of planets? Solar systems. And what's in a typical solar system? How many stars generally? 1, maybe 2, maybe 3. How many stars are in our solar system? Just 1. What do we call it? The sun. So what about other stars? Does that mean they are solar systems unto themselves with planets and moons and asteroids and comets and Kuiper belt objects? They could theoretically, and they do in some cases. But we astronomers believe that pretty much all stars have their own planetary systems. Now, you might have situations where they're binaries or multiple star systems. They're less likely, but still they could have planetary systems. So you can, when you look into the night sky and you see 7,000 stars in the night sky, each one of those is a sun, likely, mostly, with their own planets around them. 100 billion suns in the Milky Way galaxy, 100 billion solar systems in the Milky Way, 100 billion galaxies outside of the solar system, outside of the Milky Way. That's a whole lot of planetary systems. So solar systems is sort of the next level. Now, do solar systems live by themselves, or do they group together? They group together in clusters of stars that astronomers call star clusters. And there are a couple of different kinds of star clusters. You can have globular clusters that look like big, fuzzy golf balls, and then galactic clusters, which are more amorphous. But then they typically, and they have different characteristics. But star clusters typically all live together in sort of an island group of stars and star clusters called galaxies. Do galaxies live by themselves? They cluster together in what astronomers call clusters of galaxies, or galactic clusters. We don't really have inventive names for these things. So galaxy clusters. And that's right. So clusters actually cluster together in clusters of galaxies that we call clusters of galaxies, or actually we call them superclusters. And superclusters are the largest structures currently known in the entire universe. A hierarchy. That's an excellent question. That's an excellent question. So the answer to that question is, did you guys all hear the question? Because that's a really interesting question. Does dark matter have its own hierarchy? Because this is normal. This is baryonic matter. That is to say, made of protons, made of ups and down quarks. That's how we define normal or baryonic matter. The question is, does dark matter have its own hierarchy? And the answer was, we're just scratching the surface. We're just trying to figure out what it is. So likely it could. So could there be a whole dark matter universe? Does it coexist? We know it coexists to a certain extent with our own baryonic universe, but what levels do they coexist at is for generations of future scientists to answer. Good question. Okay, and I've got a slide that shows you all the different dimensions here, and I think that's interesting to learn about because it's something like 32 orders of magnitude from the smallest thing to the largest thing. But there's a couple of takeaways here. First of all, matter in the universe is discontinuous. So I can reach a fundamental point where I cannot break it down any further, and there's a fundamental building block. What about space in the universe? And what about time? Because remember, matter, all this matter and matter energy component of the universe exists within space and time. So what about time? Let's take time for example. I can take an hour and I can break it into minutes, and I can break a minute into seconds, and I can break a second into nanoseconds, and I can break a nanosecond into femtoseconds. Can I keep breaking into smaller and smaller units? Is time continuous in that respect, or do I reach a fundamental unit of time and time is therefore discontinuous? Time, like matter, is discontinuous. I reach a fundamental unit of time called the Planck time, and the Planck time is 10 to the minus 43rd of a second, so it's a tiny, 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 tiny little bit of time, but it is a fundamental unit of time. Ah, okay. Well, you can't quite measure it. It shakes out of fundamental theories about physics and cosmology. And I know that's a cheesy answer, but we can talk about it offline without having to go into another tirade. Then what about space? Yeah. Well, there's a Planck space too. So I can take a meter and I can break it into centimeters. I can break the centimeters into millimeters. I can make the millimeters into, nanometers. But I cannot break them beyond the Planck space. So there's a fundamental unit of space, there's a fundamental unit of time, and there's a fundamental unit of matter. So the entire universe is built up of these building blocks of space and time and matter.
Why can't these break down time and space? Aren't they just how we measure it?
No, they're not. They have a fundamental inherent quality that cannot be broken down any further. Yeah. So people say time is just kind of a made-up thing. No, it's really not. It's a fundamental aspect of the universe. And there's a fundamental unit of time that cannot be broken down any further. You cannot measure anything below the Planck time. That's why when you look at a chart of the Big Bang Theory, and it goes back to the Planck time, it doesn't go any further. In fact, we can't go to time zero because there really is no time zero. There's time zero really, and then there's the Planck time, and then everything is in units of Planck times after. So within the Planck time, between the Planck time and zero, we can't tell you because time really cannot be broken down beyond that fundamental unit any further. Bizarre.
Like when you say was it Planck time?
Planck. Max Planck.
Are you saying that it's like the beginning of time, or are you saying it's like a unit of time, or both?
It's really both. Okay, so if I go back in the history of the universe back to the Big Bang, right, I could theoretically go to time zero, but the smallest unit of time I can tick off after time zero is 10 to the minus 43rd of a second.
And how do you calculate that? I mean, couldn't you just keep splitting it and splitting
You can't. That's the whole point. So this is exactly what Kennedy says is exactly what is bizarre about the way that the universe is structured, is that you can't split it down anymore. There ain't no more splitting at the fundamental level. I can't split a quark. I can't split a Planck time, and I can't split a Planck unit of space. They are the building blocks. There is. That's right. That's a way to think about it. That is an implication. Absolutely. Yes, sir.
So they didn't know about quarks. They thought that protons and neutrons were
Yeah,
space.
that's right.
So is there something smaller than quarks?
Well, now that's a good question. So the answer is we haven't solved all the mysteries of the universe. According to the current standard model of subatomic physics, this is the way it is now. You know, universe is like an onion. Science is like an onion. You can peel a little bit and understand it pretty well, and then, you know, some new measurements come along and you peel a little, and that's what Jeff Crew says, life's like an onion. You peel a little bit and cry. Peel a little bit more and cry. But you guys might have noticed Jeff has a little bit of a pessimistic outlook on life, but so it could be. It's possible that, you know, there may be a new physics that comes along beyond modern physics. So you can't rule those kind of things out. Absolutely. Yes, ma'am.
So theoretically, based on these calculations, can we assume that time did not exist before?
That's right. That's exactly the implication. Time did not exist before the Planck time. It did not exist. That's exactly right. Let me get to Will, because he's had his.
Is there a proof for this that applies situation for a time? Because just thinking about it, if you know it's a situation where we had an object
Yeah.
at an infinite speed over an infinite time.
Yeah.
From a mathematical perspective,
Yes.
you couldn't break it down.
Yes. Okay. So that's a really good question, and the answer is the proof currently is not empirical at this point. It is through mathematics. The laws of physics and mathematics dictate these features, because you can't measure things that tiny. You can't measure a Planck second. What's the smallest amount of time we can measure? It would be in it's below femtoseconds probably. Well, that's right. So now you get into the quantum uncertainty when you take those kind of measurements at that level. But the fact that we know and we can measure the quantum uncertainty leads us to believe that the standard model is correct. I mean, here's the thing. It could all be like bunk, right? But you guys, when you go home, you have a television set that's based on quantum physics, that's a plasma TV or an LCD, liquid crystal exotic states of matter. Those are based on these same laws. I mean, when I go home, my plasma set works, and it's based on quantum physics. And thank God, because there's some good games on over the weekend. So yeah, I mean, you know, I'm not saying that we have everything totally worked out, but the current structure of the universe going down to the quantum level is really pretty well understood. But that's an excellent point, is that when you get down to these fundamental units, you can't see a quark, right? There's no way you can see a quark, right? Because to observe something, you have to shine a light on it, and the particle of light has to be smaller than the object, right? That's why you can't see an electron. We can barely see atoms, but it's the same kind of thing. Before we had scanning tunneling electron microscopes, people knew that atoms and molecules existed. You couldn't see them. But we had all the physics and all the chemistry and all the math worked out, and we knew they were there. And then finally later we developed the technology. And you got to tweak the models. Models are never 100% accurate. There's always an evolution of scientific models. But there's not paradigm shifts usually. In other words, you don't throw the model out because it was wrong. You might tweak it a little bit. Yes, sir.
Why can you not put down a Planck?
Okay. So the answer is why. The question is, why can you not break down a Planck second or a Planck unit of time or a Planck particle? You could consider the quark a Planck particle, and the answer is it is because it is the architecture of the universe. So to answer why, science is not really good at answering questions like why. You need to invoke your religion or your philosophy or whatever you believe in to answer questions like why. Science is really good at answering how it works, how it is the way it is. But why, that's really sort of beyond the scope of scientific investigation. So you can ask that in another class. Yes, sir, or on Sunday.
What's the distance in space in meters?
I can't remember right offhand. It's a good question. It's tiny, 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 tiny. Sorry, that's a cheesy answer. Okay, I'm about out of time, but let me see if I can end with something really interesting. Well, you can go through and look at the charts, and I've added in some details, and we could talk about the fundamental forces some other time. But oh my gosh, I didn't even get to all the stuff on what's in space, the more details of space. So okay, we can do that. I could, yeah.
That fits so well when environment.
Okay.
All of those effects like that.
Well, if I could recommend it, I think there are two pieces of that. One is sort of, you know, the solar system environment, which I'm happy to do. And then the other piece is sort of the plasma electrical environment of the Earth-Sun system. And you guys have a world's leading expert on campus that would probably be willing to come in and talk about the near-Earth environment of space, and that's your dean, Roger McNeil. So maybe I could do the solar system and beyond stuff, and then you could get him in to do the Roger. Yeah, I think he's on the schedule actually. Okay. Okay. Fantastic. Well, I think I am out of time, right? Is it 1:40?
Actually, you got about 4 minutes.
I got 4 minutes.
Yes.
Oh my goodness. Okay. Well, let me let me go through here, and then since we have some questions about the nature of space and time, and looking into distant things in the universe, let me go through and give you one last thought to think about. So, you know, we've thought about space and time as separate entities, and you know, sort of conventionally, but now you can see that space and time and matter are all sort of intertwined. If they're all made of fundamental building blocks and they all interconnect with each other, then they must be intertwined in unconventional ways. And that's certainly true of matter and energy, and matter in space and time, but it's especially true of space and time. In fact, space and time really aren't different things at all. We measure them in different ways, and we know that they have fundamental building blocks, but they're intimately related to each other because it's very difficult to separate them out. And for example, when I look out into space, I can't look out into space without looking back into time. So every time I look into the night sky, I'm looking back into the history of the universe. Now, how in the world can that be? That's right. So light travels at a finite speed. It's really fast. It's 3 times 10 to the 8th meters per second. But it's not infinite. It's finite, right? So when I turn the lights on this room, it takes a nanosecond or so to get to my eye. The room's dark until then. Extrapolate that out to greater and greater distances. If I look at the moon, I'm looking at the moon as it was 1¼ seconds ago. I don't even see the moon in real time. So it takes light at least a little over a second to get to the Earth from the moon. If you look at the sun, please don't, because you go blind. But it takes light about 8.5 minutes to get to the Earth from the sun. So if the sun all of a sudden went supernova, don't worry, it doesn't have enough mass. But if it did, you'd have 8.5 minutes to get your life in order, to get people to forgive you, to fix whatever you needed to fix, because it's all over, right? But 8.5 minutes. But if I go farther and farther out, if I look at the nearest star systems, the Centauri system, I'm talking about years now. I see that system as it was, 4.5 years into the past. And very distant stars that are still very bright, like Betelgeuse, which you can see tonight if you stay up a little bit late and look in the constellation Orion. When I look at that star, I see it as it was 1,200 years ago, because it's like literally the light that left it took 1,200 years to traverse space to get here. If I look on the other side of the Milky Way, 100,000 years ago, I mean, think of what life was like on the Earth 100,000 years ago. And if I look at distant galaxies, I can see the Andromeda Galaxy in the spring with the naked eye. And I see the stars in that galaxy as they were 2 million years ago. Human species wasn't even around 2 million years ago. Barely. We were early primates then. Virgo cluster, I can see with a small telescope. I see them as they were 60 million years ago. And extrapolate that all the way out to the most distant things I can see. I see them as they were 13 billion years in the past. Let me make one last point, and I'll answer some final questions here. So space and time are intimately related. I can't look into space without looking back into time. I have to account for this light travel time when I design communication systems for satellites. I also have to account for special and general theory, relativity theory in certain cases. So all of this sort of matters when you're designing satellite systems. But in terms of just the science, in terms of trying to understand the origin, the evolution, the history of the universe, is it a good thing that light travels at a finite speed, or is it a bad thing? Which would I rather do, to see everything as it is in real time? Which am I going to learn more about the evolution of the universe? If I see everything as it is now, light traveling at an infinite velocity, or the way it's structured with light traveling, taking time to get to places, and I can see things in the past. I mean, think about it. This is how we know so much about the origin and evolution of stars, about the origin and evolution of galaxies, the origin and evolution of the universe itself, is because the farther out I look, the farther back into time I look. And if I want to put together the sequence of events that led to the evolution of the entire universe, I just look back as far as I possibly can. And it's almost like a giant motion picture out there. The entire evolution of the major events in the history of the universe are out there for our disposal to look at. That's how we've learned what we know about cosmology. I guess I have to stop there because Professor Twiggs has come out with the cane, but I'll hang around and answer any questions that you guys may have, and maybe you'll invite me back again. Thanks.